Next example of subspace. Let V be a space given in example 9. That is the V is the space of all uh, functions, real valued function defined on closed interval AB. And W is set of all constant function defined on closed interval AB. Then show that W is subspace of V. Like this. That is W is V is a vector space of functions, all real valued function defined on closed interval AB. And W is the set of all functions, all the constant functions. That is what is the set of W? W is the set of all functions comes from the set V. Says that fx is equal to C. All for all x belongs to closed interval AB. For example, this W is what is the set of all constant function. Then we have to show W is subspace of V. So now we have to show the two conditions. So first condition is what? We have to show the addition of every two elements of W is also the element of W. So let f and g be in W, be any two elements. Then by hypothesis, by using, that is by the definition, W is set of all constant functions, and therefore fx is equal to C1 and fx is equal to C2 for all x belongs to close interval AB, where C1 and C2 are any fixed real numbers, constants. C1 and C2 are constants. Because W is the set of all constant functions. W is the set of all constant functions. And F and G be in W means F and G are belongs to W, are the elements of W, and therefore Fx and Gx are constant for all x belongs to open interval by using the definition of constant function. Now we have to show F plus G belongs to W. So when F plus G belongs to W, if F plus Gx is equal to constant, some constant. So what is F plus Gx? Is Fx plus Gx by the definition of sum in the vector space V, by using the definition of addition in V. And Fx is C1, Gx is C2, and so C1 plus C2 is new constant, and therefore it is true for all x belongs to closed interval AB. X is any element of this closed interval AB, and therefore we say that F plus G is also constant function. Hence, F plus G belongs to W because it is constant function. And therefore what do we have? Therefore we said that F plus G belongs to W for all F and G belongs to W. And now we have to show the second property. Now let K be any scalar, and then consider Kf, because we have to show Kf belongs to W. So what is Kfx? Is Kf of x by using the definition. And what is Fx? Fx is C1 and K is constant. So K into C1 is again constant, new constant, and therefore Kf is a constant function because Kfx is constant for all x in closed interval AB. Therefore, Kfx is a constant function and hence belongs to W. And therefore, the second property also true, that K belongs to W for all f belongs to W and for any scalar K. And this shows that W is a subspace of V. Okay. So, the set of constant function is the subspace of W. But observe this example. V is a vector space of all real function defined on closed interval 0, 1, or say AB, small a and small b. And W is set of all functions in V for which f of C is greater than 0, where C is fixed number in closed interval 0, 1. So this is the set of W functions in which the image of C is greater than 0 for all functions under which the image of C is greater than 0 exists in W. This is the set of the functions W. And question is W is subspace of V? Justify your answer. So W is not subspace because the second property fails for this. So as if suppose F is the element of W and then F of C is greater than 0. But if you take K as -1, then what is -1 into F? That is Kfc is -1 into F of C, and F of C is greater than 0, and so -1 into F of C is less than 0. And that is this -1 into F cannot belong to W, because -1 into Fc is less than 0, and W is the set of all functions such that F of C is greater than 0. So -1 into F, C is less than 0, and hence minus 1 into F cannot belongs to W, and so W is not closed under scalar multiplication. That is any scalar K, and the element of W, its multiplication is not necessarily element of W. Kf does not belongs to W for all K and for all F, and therefore W is not closed for scalar multiplication, and hence it is not subspace. This W is not subspace of V. But if W is the set of all constant functions in this example, if W is the set of all constant functions, then it is a subspace of V. Already these examples are solved in the previous lectures, this example. So see these exercises. V is equal to R3, the set of all order triplet or three tuples with usual addition and usual scalar multiplication. Determine which of the following is subspace of V. So for those that are not subspace, give reason. So for example, the first W, X, Y, Z says that X is 1, comma, Y is 1. So this is not subspace, because if you take 1, 1, 1, 1, 1, 0, or 1, 1, 2, and 1, 1, 0 are the two elements, then their addition is what? Is 2, 2, suppose 5. And it is not the element of W. So it is not close for addition. W is not close for addition. The answers are given. 26. No, 0, 0 is not element of W. So we can write the answer of this problem in two to three ways. That is, this is not close for addition, because if you take the two elements from this W, for example, 1, 1, 1 and 1, 1, 4. These are the element of W, 1, 1, 1 and 1, 1, 4. Then their addition is 2, 2, 5. And it is not element of W. So it is not close for addition. Also, we can show that it is not close for scalar multiplication. That is, if you take scalar 2, K as 2, and element of this W as 1, 1, 5, then 2 into 1, 1, 5, that is K into this U bar. That is 2 into 1, 1, 5 is 2, 2, 10, and it is not element of W. And we can show that this is the second answer, second method of to give the answer of that W is not subspace. Or we can give just one sentence answer, that is 0, 0, 0. This 0 bar vector does not belong to W, and therefore W is not subspace. Okay, because W, when W is subspace of V, if W is itself a vector space, by using definition, what we can say, when W is subspace, if W is itself a vector space, and when W is itself a vector space, W satisfies all the 10 properties of vector space. But W does not satisfy the property E3, that is 0, 0, 0, 0 bar. 0 vector must exist in W, but 0 vector does not exist in W, because elements of W are of this type. X and Y coordinate are compulsory one. And so 0, 0, 0 is not the element of W, and therefore W is not subspace. The answer of B is S. Answer of this B is S. X plus Y plus Z is equal to 0. This is subspace, because we know that X plus BY plus CZ is equal to 0 is subspace for all ABC. But if it is equal to 1, X plus Y plus Z is equal to 1, this is not subspace. And we have to give the counter example for either condition number 1 or condition number 2. This is also not subspace. X square minus Y square is equal to 0. Already the answer is given here. That is, give the counter example. The addition of two elements of W is not the element of W. So Y is equal to 3X and Z is equal to 5X. This is also, that is X, 3X, 5X. This is again, Y is 3X is not subspace. E, 26E, 26ES. So it is a subspace. So show the two conditions, that is addition of every two elements of W belongs to W. Then this is the F in 26F, X plus Y is equal to 0. X is greater than or equal to 0. This is again not subspace, because if X is greater than or equal to 0, for example, if you take element 1, 2, 3, suppose 1, 2, 3 belongs to W. Okay, 1, 2, 3 belongs to W. And then if you take scalar as K equal to minus 2, Then k into u bar, that is 1 1 1 2 3 into minus 2 is minus 2 minus 2 minus 4 minus 6 is not element of w, because x coordinate is not equal to 0, and so it is not closed for scalar multiplication, and therefore the second property fails for the G, and therefore G is not vectors, G is not subspace. Here is G is not closed for under closed under scalar multiplication. H not closed under addition. H number example. This fx is less than or equal to 0 is not closed for this 36 x y z, either x is 0, x is equal to y, or y is equal to z. So if you take two elements, suppose 1 1 3 and 1 5 5, their addition is not the element of w. So give the counter example. So either x is equal to y or y is equal to z. So what are the elements of w? For example, 1 1 3 is the element of w, 2 3 3 is the element of w. Either take x is equal to y or y is equal to z, or take both 1 1 1. This is also the element of this w, because either x is equal to y or y is equal to z. Means uh, if we take all three elements are same, then also it is the element of w. So take the two elements of w and show that addition does not belong to w. Let's give the counter example for the addition property is not true for w, that is w is not closed for addition. Similar examples, f0 is equal to 0, f is even function, f is odd function, f of 1 half is equal to 0, already solved this, f of 1 half is greater than 0, it is not closed for scalar multiplication, f is bounded function. So solve all these examples, the answers are given. 2 by 2 matrices, set of 2 by 2 matrices. This 27 is the V is the set of functions defined on the domain minus 1 to a1, that is a b replaced by minus 1 and 1, and V is a vector space of 2 by 2 matrices, real matrices, and the scalar multiplication, usual scalar multiplication and addition are the operation. So W is this set, A, B, C, D are integers. A, B, C, D are integers. This is not true for scalar multiplication. Already the answer is given. A, B, C, D are rational numbers. This is again rational number. So answer of 28B, 28B. No, it is not close for scalar multiplication, because if we take the root 2 as a value of k, and if you multiply, if you take the element of w and if you multiply by root 3, suppose for example root 3, then it is a not rational number. If you multiply by root 3, then suppose take a as a 1 2 3 4, and then this as the element of this w, and then root 3 into this is root 3, 2 root 3, 3 root 3. These are not rational numbers. So it is not close for a. A is a rational number. This is also not close for scalar multiplication. So A transpose is A, A transpose is minus A. Determinant of A is 0, A is non-singular. So C and D are equal to 0. C and D are equal to 0. So the intersection of two subspaces is subspace, but the union is not subspace, not necessarily subspace. When union W1 union W2 is subspace of V, if and only if either W1 is subset of W2 or W2 is subset of W1. So we'll solve this example in the next section. So the addition of two subspaces, W1 and W2 are subspaces of V. The addition of two subspaces is defined like this: W1 plus W2, such that W1 comes from W1 and W2 comes from W1 is subspace of V. So W1 intersection W2 is subspace of V. W1 sum W2, that is that sum and intersection are subspaces, but the union of two subspaces is not subspace of V. So note this thing. We will give the answer in the next discussion of this problem. So solve all these problems. So answers are given. These are the answers. So subspace of R3, we know that singleton 0, the set contains only 0 vector and itself W. Every set is subset of itself. So R2 is subset of R2 and singleton 0 is subspace of R2. So these are the two obvious trivial subspaces of R2. And lines through origin. So set of xy belongs to R square, so that y is equal to mx. Y is equal to mx. Set of all, for example, y is equal to 3x, y is equal to 4x is the set of all lines through origin. And this is subspace of R2. So subspace of R3, singleton 0, R3, that is, these are the trivial subspaces of R3. Every set is every vector space is subspace of itself. So R3 is subspace of itself. Singleton 0 is subspace of, and lines through origin. So I'll also the subspace of R3. Any plane in 3D, 3 dimension, passing through the origin is a subspace of R3. So W is R square is not subspace of R3, obviously, because R square is not subset of R raised to 3. However, the set W is equal to x, y, 0 says that x belongs to R and x and y belongs to R. So this is again the set of 3 tuples whose z coordinate is 0 is subspace of R3. It acts like R2. This is the subspace of R3, but this R2, R square is not subspace of R3 because it is not subset of R3, because this is the subset of 3 tuples. While this set x, y, 0, set of 3 tuples x, y, 0, x and y are real number, is subspace of R3. We can give the proof of this example as 2 conditions. That is, take 2 elements from W. Suppose u bar as x1, y1, 0, v bar as x2, y2, 0, and these are the element of this W. Then u bar plus v bar is x1, is the 3 tuple x1 plus x2 comma y1 plus y2 plus 0, and is again the element of W. And if you take any scalar k and any element as a u bar as x, y, 0, then k into u bar is kx, ky, 0 is again the element of W. So we can show the 2 conditions, and that's why this W is the subspace of R3. So singleton 0 and mnn. Mnn means what? It is the set of all n by n order matrices with real entries. Set of all n by n. If we take this nn as 2, 2, then it is what? N cross, right cross, or right nnr. That is, it is the set of all n by n matrices with real entries. If we take n as 2, value of n as 2, then it is set of all 2 by 2 matrices. Like this, set of all 2 by 2 matrices. This is the set, all 2 by 2 matrices. This is the set of all n by n matrices. N by n matrices. Okay. So singleton 0, that is 0 bar. What is 0 bar in the mnn? It is the 0 matrix of order n by n, and itself mn by n r is subspace of this mn by n r. N by n r, because these are the trivial subspaces. Every vector space is subspace of itself, and singleton 0 bar, that is the set contains only 0 vector from that vector space, is subspace of that vector space. So these are the obvious subspaces. Set up all upper triangular matrices. Instead of this n by n r, we take for convenience m2 by 2 r. So what is the set of all upper triangular matrices? Is the set of all upper triangular matrices mean the matrix of the type whose the diagonal element above the diagonal are non-zero, below the diagonal are 0. Diagonal upper triangular matrix means what? The matrix whose elements below the diagonal are 0. So for example, if you can write the upper triangular matrix of order 2, A, B, 0, D. So this is the upper triangular matrix. The elements above the diagonal are non-zero, below the diagonal are 0. Okay. And what is the lower triangular matrix? Is the now the elements above the diagonal are 0. It's called lower triangular matrix. Set of all diagonal matrices. When we say the matrix is diagonal matrix, if its only diagonal elements are non-zero, all the remaining elements are 0. Set of all scalar matrices. Set of all symmetric matrices. Symmetric matrix means the A11 the diagonal elements, the element of the type Aij and Aji are equal. So solve all these examples, which determine which of the following subspace of a given vector space V of a given of, if not just define. So this is the subset of R3 such that x is equal to 4y plus z, x square x raised to 4 is equal to y raised to 4. So these are the subset of R3. This is the subset of D subset of, this is subset of R2. This is subset of, these two are subset of R3. So we have to determine these are subspace of R3. We have to determine this B as subspace of R2. We have to determine this W is subspace of R raised to 4. So their answers are given. For example, the first W is the set x, y, z belongs to R3 such that x is equal to 4y plus z. So let U is x1, y1, z1. Now we have to check whether this W is closed for addition and closed for scalar multiplication. That is, we have to verify the two conditions. So first condition, for first condition, take two elements from this set W. Let W U bar is equal to x1, y1, z1 and V bar is equal to x2, y2, z2 belongs to W, be two elements. And then we have this x1, y1, z1 is the element of W, therefore x1 is equal to 4y1 plus z1 and x2 is equal to 4y2 plus z2. And then what is U plus V is x1 plus x1, y1, z1 plus x2, y2, z2 is x1 plus x2, y1 plus y2, z1 plus z2, usual addition. And now when this x1, this element x1 plus x2 comma y1 plus y2 comma z1 plus z2 belongs to W, if x1 plus x2 is equal to 4 times y1 plus y2 plus 4 times plus z1 plus z2. So consider x1 plus x2. It is equal to x1 plus x2. x1 is 4y1 plus z1. x2 is 4y2 plus z2. Take 4 common. So y1 plus y2 plus z1 plus z2. And so this element x1 plus x2 comma y1 plus y2 comma z1 plus z2 satisfies this property x is equal to 4y plus z, and therefore u plus v belongs to w. Right? U bar and v bar belongs to u bar plus v bar belongs to w. Now the second property, k be any scalar, and then ku is what? Kx1 y1 ky1 kz1. This is the scalar multiplication. Now we have to verify this element belongs to W. And when this element belongs to W, if kx1, this element satisfies this property, that is kx1 is equal to 4 ky1 plus kz1. So consider kx1 is equal to k. What is x1? x1 is 4y1 plus z1. Okay, and it is equal to 4 ky1 plus kz1, and therefore what we have, kx1 is equal to 4 ky1 plus kz1, and therefore ku bar belongs to W, because this ku bar means this element satisfies this property, and therefore ku bar belongs to W, and therefore W is subspace of R3. V is equal to R3. So similarly we will discuss the remaining example in the next lecture.